Now, let's try to derive the equation that relates between pressure with the motion of the gas molecule. So we are going to relate between macroscopic things that we can measure, which is pressure, with the microscopic things that cannot be observed easily using naked eyes, the motion of the gas molecule. So we know that the collision of the gas molecules with the container wall will result in the pressure that the gas exerts on the wall. Any pressure that is felt by this wall over here is caused by the gas molecules hitting on the wall actually. So what are we going to do to derive the equation between pressure and motion of gas molecules is, we are going to determine the change of momentum when one gas molecule collides with the wall. So if one gas molecule approaches the wall and reflects back in the opposite direction, how much change of momentum does the wall experience? Then from there, we are also going to determine the number of gas molecules that collide with the container wall. So we know one gas molecule, how much change of momentum, then we find how many gas molecules are there that will collide with the wall within this short duration of time, which is dt. Once we are able to determine both of these things, then we can determine the force exerted by the gas molecules on the container wall. Okay, so basically you just find the change of momentum of one molecule multiplied by the number of molecules that will collide within that short amount of time. Then from there you are able to obtain the force exerted by the gas molecule on the container wall. So the equation is as shown over here. You get the total change of momentum, and the rate of change of momentum is just force. Then from force to pressure is just divided by the cross-sectional area, which is the area of the wall. So now this force divided by the area of the wall, you are able to obtain the pressure that the gas exerts on the wall. So we are going to go through this step by step, starting with this one as our step 1. Okay, so the system that we're going to analyze will determine the relationship between the pressure and the motion of the gas molecule. So this is the gas system that we are analyzing, in which we have gas molecules that are moving in random direction. You have some moving directly to the right, you have some moving at the third quadrant, you have some moving in the second quadrant, you have some moving in the fourth quadrant, or even, different. All of them are moving in random direction with various speeds. But because we are analyzing pressure, we have to focus on a specific wall that we want to study. We know that all walls will experience the same pressure because the gas moves in random direction. So all walls will experience an equal amount of heating. Okay, so we are going to focus on one wall only. So let's say if we focus on the right wall, then only the component of velocity that are perpendicular to the wall will contribute to the collision with the wall. Okay, those up, down, or front, back velocity, component of velocity, will not contribute to the molecules going towards the wall or moving away from the wall. Only those that are perpendicular, going to the left or going to the right, will contribute to the molecules hitting on the wall. So we are going to ignore those component of velocity such as up, down, or front, back that are irrelevant to this collision with this wall over here. Only consider those velocity that are relevant to the gas molecules hitting on this right wall over here. Okay, so once we have ignored the component of velocities that we don't want to study, we only focus on those that we are interested to study. What we do is we can see that all of these molecules here, actually their component of velocity perpendicular to the right wall are different. Some are moving slow, some are moving faster, they all have different speed. So in order to simplify our analysis of this gas system here, we are going to replace all these different velocity, component of velocity here. We are going to replace it with the same magnitude of x velocity. Something like an average, but it's not exactly an average. Later we'll explain clearly what is this value, but it functions sort of like an average, which is a value to represent all the different component of velocities that we are having here. We replace it with one same magnitude over here. Okay, this is to simplify our discussion. Later we'll remove this assumption as well. Okay, so we have already specified what are we going to study. We focus on a specific component of velocity and we take an average value for their component of velocity. Now we can continue to study by first doing step 1, which is to determine the change in momentum of the wall due to the collision of one gas molecule with the wall. So we are going to focus on one gas molecule here. This gas molecule, all of them are moving with the same velocity. So they will be moving in this positive v. Positive means that it's moving to the right. V is the magnitude of, or the speed of the molecule. Component of speed in the direction perpendicular to the wall. All of them have the same speed, same left-right speed. But this one is moving to the right. This one is colliding with the wall. Then later it will bounce back in the opposite direction. Then it moves with the same speed. This is what we analyzed earlier when we studied perfectly elastic collision. It will move back to the same speed but opposite direction. Okay, so once we have really targeted this molecule to study, let's try to determine the change in momentum. Again, we are going to assume same magnitude of x velocity, so all of these arrows here have the same length. So the collision before collide and after collide, you have the same magnitude of velocity as well. So elastic collision, the momentum is conserved. So if you do momentum initial is equals to momentum final, and you focus on the two character, which is the molecule and this wall, you can go through this derivation here, which is exactly the same as the previous video where we studied elastic collision. Okay, from the result of this derivation, you can see that the change of momentum experienced by this wall is equals to 2 times the mass of the molecule multiplied by the speed of the molecule. Okay, so this is similar to the momentum of the gas molecule. 2 times the momentum of the gas molecule will be equal to the momentum, change of momentum experienced by this wall over here. But this one is the change of momentum experienced by due to one single gas molecule only. Later, we need to determine how many gas molecules will be hitting on the wall per unit time. Then from there, we determine the total change of momentum. Okay, so this is step 1. Step 2, we determine the number of gas molecules that collide with the wall within this short amount of time, delta t. Okay, so this is the wall that we're interested in. We want to study how many gas molecules is going to collide with this wall within a short amount of time. Okay, so there are n gas molecules in the container of volume V. Okay, so this is total number of gas molecules, big N. Since the gas molecules are moving randomly, we deduce that the number of molecules moving to the left and to the right should be the same. So let's say if we have 1 million gas molecules moving inside and they're all moving randomly, through kinetic molecular model, we say that they're moving randomly. That means that if we have 1 million gas molecules moving around, you can assume that 500,000 of them will be moving to the right, 500,000 of them will be moving to the left. It's just probability. You can assume half of them is left, half of them is right. Okay, so you can say that the number of molecules moving to the left will be equal to the number of molecules moving to the right, and it's equal to the half of the total number of gas molecules. Just like what I say, if you have 1 million molecules inside this system, 500,000 will be moving to the right, 500,000 will be moving to the left. Okay, so only molecules moving to the right can collide with the right wall. Okay, for those molecules that are moving to the left, it's impossible for them to collide with the right wall at within that amount of time. So since all molecules are moving with the same speed, as we assumed earlier, they are moving with the same speed, they travel the same distance d, okay, which is taking the speed multiplied by the duration of time to the right. Okay, we say that all of them, we assume them to move with the same speed, and we are going to ignore those molecules that are moving to the left. So we only focus on those molecules moving to the right, and we should expect that after a short amount of time, delta t, they all should move the same distance to the right because they have the same speed. We assume them to have the same speed. Okay, so this is a drawing of all the molecules that are moving to the right, and we can see that all of them move the same amount of distance to the right because they all share the same speed. So the amount of distance traveled by all these molecules moving to the right will be the same. But in order for you to hit this wall, this particular wall over here, you can see that only the molecules in the pink region is able to hit onto the wall. Those molecules which are initially situated in the yellow region here, they are not able to reach the wall because the amount of distance they travel is not enough to hit the wall. Okay, whereas those molecules that are in the pink region, if you look at the distance traveled by these molecules over here, you can see the distance traveled is just enough or more than enough to hit this wall over here, and it will reflect back, of course. Okay, so this distance here will be the distance this minimum distance, okay, this distance over here will be calculated using the speed multiplied by the duration that we mentioned earlier. So if you're within this region, then you know that the travel distance by this molecule will definitely hit on the wall. Okay, if your distance is less than v times delta t, then you definitely hit the wall. But if your distance from the wall is greater than this v times delta t, if you are situated around here, you know that by the time you travel that amount of distance, you are not able to reach the wall yet. So you have to be within this region where the length is v times delta t in order for this gas molecule to hit on the wall. Okay, so that's the idea. So now, only right moving gas molecules in this pink region here can collide with the right wall within duration delta t. If you are a gas molecule that are outside this region, you are not able to reach the right wall within delta t because you are out of reach. You cannot reach the wall within this short amount of time, delta t. So we need to find the number of right moving particles in this pink region over here. So how many particles are there in this pink region? That is what we need to find out. Okay. So within the duration dt, we are going to change it to dt just to make the calculation more accurate. Okay. You know that the total number of right moving molecules in this container will be all the molecules that we are seeing here. Okay, but how do we isolate those molecules that are in the pink region? We take the total volume of the gas system as the denominator, then we take the pink volume over here as our numerator. So from there, if we know how much is the pink volume, how much is the total volume, then we put it as a fraction. From there, we can know that 20% of the molecule are in this region. So we are able to know 20% of the total number of right moving gas molecule will be the number of molecules that hit onto the wall within dt. Okay, so you get the whole volume of the container as the denominator, which is yellow plus pink. Then you get the volume of the pink region as the numerator. So from there, you get a fraction that show you how many percent of the total amount of gas molecule that are moving to the right will be hitting on the wall. You get a percentage, or you get a fraction of it. Okay, so we know that the total number of gas molecule moving to the right is half, because you know that half of them is moving to the left, half of them is moving to the right. Then the volume of the container V is just V. That one is just a whole volume, the volume of the whole container. Whereas the volume of the pink region, we know that it's this cross-sectional area, this area here, the area of the wall, multiplied by this height over here, which is V times the dt. So we can get the area multiplied by V times dt, then you get the area, and you get the volume of this pink region over here. So again, this is the pink region, this is the whole volume, then you multiply by half of the total number of molecules, because only half of them is moving to the right, half of them that are moving to the left, we are going to ignore it. Okay, so from there we are able to determine the number of gas molecules that collide with the right wall within this short amount of time dt. And the number of molecules is represented by the total number of gas molecules multiplied by the area of the wall that we're interested in, multiplied by the average, it's not average, but the currently we call as average speed, multiplied by the duration, divided by 2 times of the total volume of the gas system. Okay, so now we already determined the number of gas molecules, and you already determined each molecule how much change of momentum they experience. Multiplying them, you get the total momentum. Then from the total momentum, you know that the rate of change of momentum is just a force. Okay, so you know that force experienced by the wall, okay, or you can say force exerted by these blue gas molecules here. The force exerted by these gas molecules here on this wall will be equal to the dp dt, which is a change of momentum on the wall divided by time. So the change of momentum on the wall, it has to be total. So it means by you have to include the change of momentum due to all these blue molecules over here. Okay, so that will be equals to the number of molecules that will collide with wall A here within delta T, multiplied by each molecule, how much change of momentum they exert. Okay, so this is the number of molecules that we determined from step 2 just now. This is the number of molecules that will collide with the wall within time dt. They multiply by each molecule, how much change of momentum they cause to the wall. So from there, you are able to get the total change in momentum of the wall. Okay, so if you simplify the equation, multiply everything together, you can see that dt, yeah, you can cross out. Then from there, you are able to get this equation, and then A, V squared divided by V. So this is a force exerted by the gas molecules on the wall. Again, this is the equation, but it's still halfway. Our final destination is pressure. We have the force right now. So by taking this force divided by the area of the wall, I believe you know that you will get force divided by area, pressure. Okay, so now you determine the pressure that the gas exerts on the wall. So this is just force divided by area, as we mentioned just now. So you can see the area will cancel out. Then you get the equation for pressure. So this is the equation for pressure, and technically we are almost there already. But as we have said earlier, we are only focusing on this right wall over here, and we are only focusing on molecules that are moving to the right. Later, we need to generalize this equation to consider the 3 dimensions, because you still have the top wall, you have the bottom wall, you have the front wall, back wall, and the left wall. How are you going to generalize it is our next step. Okay, so this is the equation. What we are going to do is, because you can see that square will make everything positive, so there's no purpose of putting a modulus already. So we are going to remove a modulus and just call it as Vx squared. And I believe you can start to remove the assumption that all molecules in a gas have the same magnitude of velocity Vx. okay? And you are going to replace this Vx squared with Vx squared average. Okay, the idea is previously, if you choose to put average at this point over here, if you choose to put average, only you square it. The problem is you have molecules moving to the left, you have molecules moving to the right. Okay, if you have molecules moving to the left, you assume them to be have negative x component of velocity, whereas moving to the right, you have positive x component of velocity. So if you average them before this, you get a value of 0, because -5 and +5, if you average it, you get 0. That's the problem. But now you can see that this equation here, at the end of derivation, we see that there's a square here. So if you have -5, you have +5, you square it, both of them will be positive. Then now, if you choose to replace this value here with an average, you won't get an average value of 0 right now, because the square value must always be positive. So if you get all positive value to find average, you won't get 0. Okay, previously before there was a square there, if you choose to make an average at that point earlier in time, you choose to take average of Vx, the problem is you have negative x component and positive x component. So if you average, you get 0. Then the equation will not be functional anymore. But now we see that there's square, so it's a good opportunity for us to replace it with an average right now. So now instead of finding the average of V, what we are finding is we are getting the average of V squared right now. Okay, so V squared will not get a 0 for its average, because squared value must be positive. So now this will, we are going to replace it properly with an average. So now it becomes V squared average, but there's an X component because we are still restricting the discussion to this right wall over here. Okay, I hope I make it clear why we are not doing the average earlier, because if you're doing average earlier, you get 0. But now there's a square, is a good opportunity to take an average after you square it. Okay, because after you square it, every value will be positive, average it, you will still get the value which is non-zero. Okay, so now we continue. We are going to generalize this motion in 3 dimensions. Previously, we are focusing on only the speed that is moving to the right, but there's also the top wall, the bottom wall, front wall, back wall, and the left wall. So how are we going to generalize it? Well, we know that a particle can generally move in 3 components of velocity: the Vx, the Vy, and the Vz. Okay, so you know from Pythagoras, the Vx squared plus Vy squared plus Vz squared. If you square root, then you get V, right? Okay, but if you remove the square root, then you get this equation: Vx squared, Vy squared, Vz squared is equal to V squared. Okay, so we expect that particles, they are not influenced by gravity, so they will not be pulled downwards by gravity. There will be no other forces that are affecting them. They are moving independent of all the other forces. They are just moving around in a straight line. So if that's the situation, we should assume that motion to the left will be similar to the motion to the right. Motion up and motion down and motion front and motion back should not have any difference, because there's no like gravity trying to pull everything downwards, and there's no like vacuum trying to suck everything upwards. So every dimension should be identical. No matter you're moving to the left, you have equal probability of moving to the left compared to the right. You have equal probability of moving to the front compared to the back. You have equal probability of moving upwards compared to downwards. So every direction of motion is equal in terms of probability. So they should behave the same way in all 3 dimensions. Any direction is equally possible to move. So because of that, right, we can assume that the average speed for x, average speed squared for x, and the average speed squared for y, and the average speed squared for z should be the same, because it's the speed you should get for x and the speed you should get for y and the speed you should get for z should be equal, because there's no gravity trying to pull it to a certain direction. Okay, so because they should be equal, we can take this equation and assume all 3 values here are the same value. So we can replace everything with just x. You can replace the y with x, you can replace the z with x, because they all have the same value once you square and average it, because all sides, all dimensions are equally probable. Okay, so now you can see that they are all the same, so I can change it to become 3 times of Vx squared average is equals to V squared average. So now what can I do? I can say Vx squared average is 1 over 3 V squared average. Why do I do that? Because by doing so, I'm able to change something which is focusing on the x component. I'm able to generalize it into 3 dimensions by considering that all 3 dimensions are equally probable to move, and they should get the same squared average. Okay, so now this is the equation that we get from step 4 just now when we determine the pressure. but it's still restricted to the x component as of right now. So what we're going to do, we are going to replace this Vx square average with 1 over 3 V square average. Now you have already generalized this equation to 3 dimension by not restricting the equation to the x component only. Okay, but once you have reached this part, actually this V square average here, we are going to V square average here, if you square root it, you are going to get something called root mean square speed. Okay, you can see root mean square speed, it starts with square, then mean, then root. That means by you square the value first, then you find the mean, which is the average value. Then the third step, you find the square root of the mean squared value. So by seeing that, V square average here can be replaced by taking this equation, square both sides. So this will be VRMS square is equals to V square average. So we are going to replace this V square average here with VRMS square. So this is how we get the equation P is equals to 1 over 3 and M VRMS square divided by V. Okay, I will wish to explain clearer what is root mean square speed. So here, let me write it down what is root mean square speed. So basically, you have all the molecules here. They are all moving in different direction and they are all moving with different speed. Okay, so you have some which is moving slow to the left, you have some which is moving fast to the right, you have some moving slow to the front, you have some moving fast to the back, you have some moving fast upwards, you have some moving slow downwards. They all have different speed and they all move in different direction. So as I mentioned just now, if you just take average speed, what happens is the slow to the left will cancel out the slow to the right. The slow upwards will cancel out the slow downwards. The fast front will cancel out the fast back. So at the end, if you find the average of all the molecules, the average speed that you get, it will be 0. Because they all have different directions, so the negative will cancel out the positive. That's the problem. But by using root mean square speed, what we're going to do, we take the speed that we said earlier, no matter you're negative or positive, front, back, left, right, up, down, what you do is you square the speed first. So if you square the speed, essentially what happens is you make all the negative value to become positive value first. Okay, once the value is positive, then only you try to determine the average of the speed that is already squared. So because it's positive already, if you find the average of all positive value, you will not get back 0 anymore. There's no negative to cancel out positive anymore. So the result of the average of something that is squared will be a non-zero value. So once you already find an average of it, you have to neutralize back the square that you have done earlier. Okay, the purpose you do the square is because you want to remove all the negative sign, but now you have to cancel out the square effect back. So what you do is you square root the value back. Okay, so that's why you start with square, then you average, then you find the root. So the name of the thing is called square, then mean, then root. That's why the name is called root mean square. Start by doing the square first, then average, then you root it back. That's why the name is called root mean square speed. Okay, the purpose of us doing root mean square speed is because gas molecules are moving randomly in all directions. So if you find the average of velocity, it will be 0, which is not meaningful. Again, left, right cancel, up, down cancel, front, back cancel. Square, you remove the negative sign that indicates direction, everything is positive. Finding average will not be 0. So if you find an average of squared value, you have to cancel out the square effect. That's why you square root it back. Okay, so that explains why VRMS is equals to this thing over here. So if you square both sides, you get VRMS square, it's just V square average. That's why you're able to replace this V square average here with VRMS square. Okay, so that's basically it. So we have already derived the equation, which is P is equal to 1 over 3 and M VRMS square divided by volume. This equation here can relate between pressure, which is something that you can measure macroscopically, with the motion of the gas molecule, which is represented by the root mean square speed. So something macro can now be related to something micro, and actually we can further manipulate this equation by rearranging it, putting PV to one side, and you have 1 over 3 and M VRMS square on the other side. This arrangement, it makes more sense because we know about ideal gas law. So PV is equals nRT, then it allows us to manipulate this equation further. That's why we arrange it like this. Okay, this is still correct, but if you rearrange it, it will make more sense. Okay, another way of manipulating this equation is by saying that the density of gas is equals to the mass divided by volume, right? So if you know how many gas molecules you have, multiply by mass of each single molecule, what you are getting here is the mass of a system, which if you divide by the volume, you will get the density of the gas system. So NMV exists here, NMV is over here. So what you do, you can replace this NMV with rho. So the equation will now be pressure is equals to 1 over 3 rho Vrms squared. So from here, we already derived the equation that relates between pressure and motion of gas molecule by relating pressure and Vrms, by relating between pressure and Vrms. And that's how we relate between macroscopic properties and microscopic behavior of gas molecules.